Hey there. Today we're going to do a video that we look at estimating a linear demand model where we have demand and the number of units that customers have purchased on average at a variety of different prices, right? This might be our data that we've collected over time at various prices, or it might be data that we've purchased, some point of sale data where we've looked at a similar product to ours and how demand and units purchased change as the price changes. And so what we want to do is figure out a linear model so that we can try to predict how many units will sell at different prices. So we're going to do this in 5 steps. First, we're just going to calculate some basic descriptive statistics, like how much we've sold on average, what price we've charged on average, what our standard deviation of our demand is, and what the minimum and maximum number of units demanded has been. And then after that, we're going to plot the data, find some slopes and intercepts, and we'll use that to forecast sales for next period. And then we'll take a minute to just answer the so what question, right? So what? What exactly have we done and what can we learn from it? And I'll spend a minute doing that. And then that should help you get ready to do the assignment that is required in the next 2 tabs. Okay. So the first thing is calculate some basic descriptive statistics for the data. We want our average demand, our average price, we want our standard deviation of demand, minimum and maximum levels of demand. So I'm going to come over here and I'm just going to merge these 2 cells and I'm going to enter a label for what I'm doing. I'm going to call it descriptive statistics. And then I'm going to calculate the average demand, average price, the standard deviation of demand, and then minimum demand and maximum demand. And I'm going to use some basic Excel formulas to do this. For the averages, it's just the formula is average. And if I want average demand, I'm going to highlight the cells from B10 to B26. And the answer there will be 90.1. That's the average level of demand that we have seen in our data at prices ranging from $6 to $10. The average price that we've charged, or that we've seen charged, if this is not our data, on average, the price has been $8 per unit. The standard deviation of demand, when you start to enter STD for standard deviation, you get some choices, population or sample. I'm going to use sample because I'm assuming this is not all of the data that ever has existed on this. It's just a sample of that data. 1.72 is the standard deviation, and then our formula for minimum is equals min, and our formula for maximum is equals max. And then I'm going to just format these so that they have 1 or 2 decimals. Let's do 1. Okay, perfect. Those are our basic descriptive statistics. What this tells us is that on average, 90.1 units were sold when prices ranged from $6 to $10, and the average price was $8, right in the middle. The standard deviation of demand was 1.7, which gives us a sense of the distribution of the data, and demand ranged from 87.9 to 94. So let's next move to the next step where we're going to insert a scatter plot of the data. And then we're going to format the chart so that if someone's looking at your chart, they don't need to ask you any questions. We're going to adjust the axes and we'll label them, we'll title it. And then we'll put a trendline equation in R squared on the data on the plot so that we can see what the slope and intercept are. And then we're going to just make it look tidy because tidy goes such a long way with plots. So the easiest way to do it, when you've got your X and Y variable and they're right next to each other, you can just highlight all of the data. And then under Insert, you want to choose a scatter plot. XY scatter, and we're just going to do a regular old scatter plot with no lines connecting the data. I'm going to move it here. So a couple of things that I see right away is that if you didn't know what this plot was of, you wouldn't know what the heck was going on. And all of our data is bunched over here. I'd like to just get rid of this white space so that our points fill the whole screen. So let's do that first, and then we'll title it and label the axes. So if you double click on that axis, an option, this will come up that says Format Axis, and I'm just going to adjust the minimum and maximum. So I'm going to start, our lowest price is $6, so I'm going to start at $5.50, and our highest price is $10, so I'm going to end at $10.50. And then I want to come and change this title so that if I look at this, I don't have to question what's going on. So I've got demand in units. Actually, I'm going to call it units purchased or units demanded at prices from 6 to 10. And then so that we know what's going on, I'm going to add some chart elements, which is under the chart design tabs. If you're on a PC, there's a little plus here that you can click and it's a lot easier. I'm going to title my axes by entering a horizontal axis and a vertical axis. On a PC, that's quicker. But here I'm going to call this units sold. And here I'm going to call this price per unit. Cool. All right, now when you look at this graph, you know exactly what's going on. We know we've got price on one axis and then units sold, which is an important distinction because demand can be expressed in both units and dollars. And so you want to just know what you're dealing with so that you don't then confuse this and think that's how many dollars worth of, cookies or whatever it is you sold. So then I'd like to get a trend line that will plot the line that best fits the data, because that line represents our forecast of demand. If we think that there's a linear relationship between price and demand, we can use the equation for that line to forecast demand at any price within the observed region. So to get that trend line, you just click any one of those dots. You can see that they don't all light up, but that's okay. And then you right click. And you want to do add trend line. It might say insert trend line if you're on a PC, but it doesn't matter. That's the idea. Add a trend line, and then this box comes up, and we want to display the equation and display the R squared. And then you want to grab that equation and move it out of the way. Get it out of there. That way you can see it. And so what the equation in this box tells us is that our Y value, which in this case is units sold, it's going to be equal to a negative 1.199x plus 99.651. And that basically just means that the intercept here is 99. So if price were 0, which we can't actually extrapolate that far because our lowest price is 6, but on this line, at a price of 0, demand would be 99.651. And then the slope of negative 1.199 tells us that for each dollar increase in price, we're going to sell 1.199 fewer units. All right, we can see that the relationship between demand and price is negative. At higher prices, we sell fewer units. And at lower prices, we sell more units. And that slope, negative 1.199, basically quantifies that number, the way that sales decline as price increases. So we're going to find those coefficients again, that slope, intercept, and the R squared. We're going to do it again, but we're just going to plug it in here. So we're going to use it, we're going to find those using the Excel functions. So the Excel functions, we're going to start with slope, and we're going to do intercept, and then we're going to do R squared. So the slope formula is slope. And then it wants you to input the values that you know that are on the y-axis and the values that you know that are on the x-axis. Well, in this example, we've got our prices on the x and our demand on the y. So for known y's, we're going to choose demand. And for known x's, we're going to choose price. And here we have, I'm going to change the decimals so that we have the same number of decimals that's shown on our chart here. But then we have the same slope. We find that both ways. That is one hint that you've done it right. Price is on the x, demand is on the y, and those two slopes should match. Intercept formula is equals intercept. And again, the known y's are demand, and the known x's are price. 99.651. And then the r squared, RSQ, known y's, known x's. This nifty little statistic, r squared, it can be expressed as a decimal, but you could also express it as a percent if you wanted. And the way you can interpret it is to think that the r squared tells us how strong, in some ways, the relationship is between the x and y variables. So in this case, how strong is the relationship between price and units sold? More specifically, it's what percentage of the variation in demand can be explained by variation in price. And so we can see that demand varies a lot, right? It varies from 87 to 94. And the r squared tells us, well, what percentage of that change is explained by changes in price? So 77% of the variation in demand can be explained by changes in price. And so that's a pretty strong relationship. So if we move to the next step, we're forecasting next period's sales, and let's just assume that we charge the average price. So I'm going to call it forecast at AVP, forecast at average price. So what we're doing here is we're trying to say, if we charge $8, what do we forecast that sales are going to be? And because we're using a linear relationship, the forecast is going to yield a point on that line, right? So you can kind of eyeball it. At $8, the forecast is going to be on that line. It looks like it's going to be almost exactly 90 units. So let's enter our slope-intercept formula and see what number we come up with. So to do that, we say that it's going to be equals to the intercept plus the slope times our average price. Not in dollars. Don't leave it in dollars. Be really careful because you don't want to confuse sales in dollars with sales in units, right? You want to be able to come back to this later and know exactly what you did and not have to retrace your steps. So our forecast at our average P is 90.1. We can contrast that to the actual number of units sold at $8, which was 89.4, and those numbers do not have to line up. Because when we have a linear model, we know that any model is just a simplification of reality that we use to try to improve decision making. And here we can see that at $8, we actually sold a point that lies below that line. Our forecast would have been, $8 right there. There we go. Would have been 90.1, although we actually sold on average 89.4. It's because there are a variety of things besides price that impact demand, and this model only takes into account price. So the last thing, and then my instructions say round to the nearest whole number. Let's follow the rules. Then the last thing I want to do is just to take a second and explain to ourselves what the heck did we do, right? So insert a text box below your plot, write a brief description of your model, discuss the slope, I have 2 commas there, r squared, and your forecasted demand. So under insert, we're going to insert a text box, and I'm just going to use this space. And then briefly, so what, right? What is going on here? So we basically created a demand model. And our demand model shows that at higher prices, we sell fewer units, and at lower prices, we sell more units. We can sum that up by saying that the relationship between price and demand is inverse. So right, we have an inverse relationship between price and units sold. The number that best quantifies that relationship is, in fact, our slope. The slope tells us to what degree demand changes when price changes. our slope of negative 1.199 tells us that on average, a $1 increase in price will cause demand to fall by 1.199 units. You know, of course, this goes the opposite way. If we decrease price by $1, demand would rise by 1.99 units. And the other thing we can see with the R squared of 77.24 is that the relationship between price and demand is pretty strong, right? Changes in price is responsible for 77.2% of the variation in demand. So our R squared suggests that the relationship between price and demand is pretty strong. 77.24% of the variation in demand can be explained by variation in the price. And then the other thing that we want to talk about is our forecasted demand, because we're forecasting 90, and that number differs than the actual amount observed. And so let's just explain really quickly why that might be. Our forecast for demand at the average price of $8 per unit is 90 units. This number is greater than actual average demand at this price. This can be explained, well, let's not even say that. You know, what are we going to say? We're going to say that's okay. That's okay. While our model, you know, is a representation of reality, and it explains 77% of the variation in demand, there's 23% of the variation that price doesn't explain. And so we can see that not all demands, in fact, very few, actually line up perfectly with our forecast. So we're explaining 77% of the variation using that line. And so we don't expect our forecast to match up with actual demand because we're not explaining all the variation. There's so much of it that we can't explain, right? That's okay. Our model explains 77.4% of the variation, 77.24% of, oh, look at that, excuse me. But typically, actual demand will differ slightly from our forecast. Boom, that's what I'm calling it. Okay, so that's how I would approach this question. And you can use that same method to solve the problems on tabs 1 and 2.